Emmanuel, let me know when you'd like me to start. I can't see you.
By all means, please start.
Oh, okay. Sorry. You're sitting here watching me look around. All right. Good morning, everybody. Thank you for allowing me to do this via Zoom. I imagine that you've had enough of that in your lives over the past couple of years. So as Colin mentioned, what we're going to do for the next lecture before lunch is take everything that you've learned about how to measure some of these metrics of phytoplankton community composition in the field, and then try to bring them up into space. I have a troubled relationship with this topic. On one hand, as the project scientist for PACE, I'm responsible for a mission that promised an ability to derive phytoplankton community composition from space. I've also published it. On the other hand, having seen how the sausage has been made, I'm skeptical of it. And I think there is a fair amount of work that remains to be done, which is why we added this component to this class, because you, the next generation, will hopefully pick up the ball and run with it. And so in trying to reconcile how I felt about all of this, when rereading 1984 a couple of years ago, you of course come upon the term doublethink. I'm not sure if you're familiar with it or not, but if you are or are not, it is the act of simultaneously accepting two mutually contradictory beliefs as correct. And in the context of this kind of remote sensing, the example would be advanced ocean color missions like PACE are finally going to allow us to identify phytoplankton community composition from space. And I take that to management, and we write papers on it as a community. We get new missions and life is good. But the contrary position is ocean color approaches to identify these communities are limited in their abilities and performance. So you're really kind of talking out of both sides of your mouth here. Now, I don't think any of you would be here if you weren't positive about the ability to do this. I imagine many of you are studying it. That's great. Keep that enthusiasm up. But most of this talk is going to try to walk through the existing capabilities that are out there, and then focus on the second half on the limitations and the gaps, so that we can have a more serious conversation, within this class or as a community, as to what has to happen next to get better at all of this. So 2 slides on resources I'm sure many of you are familiar with, but if not, here they are. The IOCCG, the International Ocean Color Coordinating Group, did host a PFT, phytoplankton functional type working group a few years ago, and they came out with 2 different reports. You'll have copies of this, so you can chase them down if you're not already aware. Then I'm sure also, as most of you are aware, there were 2 very nice summary papers that appeared in Frontier Marine Science in 2017. Worth checking out if you haven't seen them. There's been work since then, but these were a nice benchmark at the time. And they went a long way into identifying major gaps. Of course, they talked about mismatches between what you're measuring from space, what the models are doing, and what you're measuring in situ. We'll discuss this a little bit today. Lack of quantitative uncertainty estimates, we'll get to that as well. Spectral limitation of current sensors and regional applicability, which Colin touched on very nicely in the previous lecture. And then the recommended actions are pretty much what you might imagine they are. We need to talk more about this. We need to get the community more engaged in this. We need to have more field campaigns. We need different instruments. We need new algorithms. Really soup to nuts. So helpful to have on paper, but in practice, where do we go from here? So the general perspective of the talk and my personal approach to all of this is that we're surrounded by believers and non-believers. But you do need to know from remote sensing that this is pushing the boundaries of anything flying right now. In fact, it's pushing the boundaries of things that are being designed to fly. As you just learned from Colin, it's pushing the boundaries of what you can measure in the field. Lots of methods have been proposed. Most fall into 2 classes. This is the remote sensing concept. You're not really surrounded historically by an abundance of spatially and temporally diverse data that is starting to change with new in situ technologies. But whether you like this or not, whether you're a believer or not, this is the future. So get on board and help out however you can, even if it is to maintain caution, fill in gaps, point out deficiencies. This is very important. As I mentioned, it's a huge science driver for new missions, and we're going to go through methods and issues. So I don't know how interactive we can be, and I usually like to walk back and forth. So I will apologize if I'm just reading to you, but this is where I would start asking your opinion on this. That said, I believe you're savvy enough now that you probably have an opinion on this. So why is it more difficult? Why are there more challenges in doing something from space that revolves around phytoplankton community composition relative to chlorophyll? Well, there are a lot more methods to do this. And so there's been a ton of convergent evolution over the past decade. And as you'll see in the coming slides, the diversity in the methods is out there. And that's in terms of approaches, products to use, even units in terms of what the satellite algorithm is producing. So that's hard to reconcile. So there's a ton of in situ methods to infer community composition. They don't always agree. They sometimes agree. There's not a lot of studies out there that actually do intercomparisons rigorously. Big gap. And then what we'll talk about next slide is the increased degrees of separation between the satellite and the in situ measurements. Not the next slide, sorry, one coming up. Terminology you already know from the previous talk. PSC, it refers to particle size class. That can be a particle or phytoplankton. And then a functional type. Well, function can mean lots of different things, and the algorithms reflect that. They all have different goals. All right, back to the degrees of separation. So when you're doing a comparison of a satellite ocean color remote sensing product, really what you're getting to is remote sensing reflectance. And you can measure that almost directly in the field. So there isn't much of a degree of separation. Yes, as you've seen this week, and you've heard in the other satellite lectures, there are a lot of nuances in this. But effectively, once you get down to the derivation of the product, you're looking at the same thing in principle. This increases by 1 degree from the satellite end of the spectrum when you're thinking about how to compare a satellite measurement of chlorophyll or IOPs. The satellite only measures light. It does nothing but measure light. But we're pretty good at modeling chlorophyll and IOPs, and you can make direct measurements of this in the field in the laboratory. When you're getting into phytoplankton community structure, you're taking one more step from the satellite end most of the time. You need an intermediate chlorophyll or inherent optical property to get to your size class or your functional type. And historically, as again, you just saw from Colin, you're not really measuring PFTs or PSCs the same way in the field. And so you can see by the spread of this as it grows, there are a lot of things in the way, or a lot more degrees of separation in what you're actually trying to infer here. Now, we do want to make a nod that over the decade, there has been a lot of evolution where you try to go right from remote sensing reflectance system, functional types or size classes. And in situ measurements have exploded in their utility and the way that they're being used. So you're doing this a lot more elegantly or directly, but again, a lot of work still remains in relating the two. So first thing we're going to talk about, and this will be the first half of the remaining part of this lecture, are what are the biooptical methods that currently exist to get to size classes and PFTs. And recall that all ocean color approaches fundamentally start with just remote sensing reflectances. I would put just in quotes because it takes a lot of work to get to remote sensing reflectances, but at a fundamental level at the sea surface, this is what the satellite sensor is providing you. So we're going to review retrievals of size classes and functional types using only what's available from satellite ocean color, which is remote sensing reflectances and products derived from that. All right, so we're going to go down and get back to the 2 flavor algorithms with various inputs and outputs. This is intentionally intended to be a spaghetti plot. I want you to sit back and watch how many different approaches have actually been realized over the past 2 decades or so. And note also that they don't always retrieve the same geophysical data product parameter. Some get to concentrations of accessory pigments, some get to the size classes we're talking about, some get to functional types. And even within functional types, it varies wildly what they're trying to get towards. So you could start with just satellite measured radiances, and there are approaches to do all of three of these, to derive all three of these data products. There are approaches that take satellite derived chlorophyll and derive all three of these data products. There are approaches that take satellite derived absorption and get to all three of these data products. There is a more limited number that use backscattering, and they typically go right to size class. Sometimes you throw absorption in with backscattering, and you can get to size classes. And then you can use combination of all of these things, where you're taking the radiances and derived all IOPs, and there are methods to get to all three of these products. So how do you choose between these? What is the best approach for your application? Well, we'll get to that. I think there's a lot of thinking you might need to do depending on your application. But let's start with just thinking about fundamentally, how do they work? And then maybe that'll guide you into your thought process in terms of choosing. And these categories of flavors of algorithms generally fall into either an abundance method bucket or a spectral method bucket. All right, so pausing for a second as we start to go through all of these. When this lecture was first introduced in this class in 2011 or 2013, there were really a dozen or so core approaches to do all of this. And I'm sure many of you are familiar with them, or if not, you're familiar with the more advanced approaches that have since been produced and revealed. But there are too many to go through in this talk. Just so you get a sense of the explosion of approaches here, last week, a Google Scholar search for phytoplankton functional type in quotes yielded almost 500 results. And if you add ocean color to the beginning of that, and then in quotes put in community structure or community composition, you have over 4,000 results. I think one of those two yielded almost 6,000. What this indicates is it's a booming business for algorithm development, and even more so for how the data are being used, how these products are being used to interpret things. So we're only going to cover several heritage examples, but I want you to get the take-home message from this, that there is a diverse array of methods that are out there. Because of this, you are going to need to have a critical eye to select or create your own to best approach whatever application you have in mind for your future work. My personal opinion on this, and I think this is shared, is a ton of progress has been made. We can't minimize how much investment has been made to get to where we are, but yet we're still at the point where most approaches are either A, doing it wrong, or probably more importantly, they're not telling you what they think they're telling you. And I think that's the hardest part you're going to have to unravel as you go forward. And as we have hyperspectral instruments, and so we bring instrument environmental data and we use new machine learning techniques, what are these approaches actually telling you? Is it what you think it is? All right, back to the categories. If you have interest in references beyond what we go through today, there are the two papers that I mentioned earlier, both have tables that also highlight the abundance of spectral approaches, and they have references in there. So at least as of 2017, they're a good resource for you. Okay, jumping into abundance methods. Abundance methods assume that if you have a singular given phytoplankton biomass, that's either defined by an IOP or a chlorophyll concentration. And usually when we're talking about IOPs here, we're referring to phytoplankton absorption, that this biomass covaries with a dominant functional type or size class. So two examples of that for you. The first is going to be using satellite-derived chlorophyll to get either a size class or a taxonomic community. And one of the earliest of these, it comes from Takafumi Harada. So this is a 2011 paper. I would also refer you to the work by Julia Wheats, which is very good here. And the purpose of this research was to provide an estimate of the percent chlorophyll for a variety of different functional types or size classes. So there are a number of in situ data sets out there that provide in situ measurements of HPLC. And so what Taka did, that used the Nomad data set, which had coincident measurements of total chlorophyll A and all of the accessory pigments that Colin talked about, and used diagnostic pigment analyses to relate statistically the fractions of his DPA derived size classes and phytoplankton communities as a function of total chlorophyll. The reason he did this is he knows he can get total chlorophyll from a satellite estimate, and using all of these empirical statistical regressions, he was able to come up with relationships between chlorophyll and size classes. So in this case, what you can see is the line here basically suggests as chlorophyll is increasing, the relative contribution of picoplankton is decreasing. Probably fairly intuitive. Then of course the opposite is true of microplankton as well. He went further to divide these by species and then create similar relationships for chlorophyll for different functional type groups. And the nice thing about this is it's very simple and straightforward, and you can create these beautiful satellite maps of distributions, relative percent distributions, which you can see over here on the left side, based entirely on chlorophyll. So given what you know about remote sensing of chlorophyll and the physical measurement of chlorophyll, and then the measurement of all of these high performance liquid chromatography derived pigments, and then the DPA and Chemtex analyses that go into all of this, think about whether or not you trust this or not. I'm not saying it's not heroic, it's a great step, but think about it. Taka did some groundbreaking work doing absorption as well out of the same lab. And in this case, it was to assign a dominant size class to each satellite pixel. In this case, it was in situ measurements of absorption spectra that were considered. The premise is that the slope of phytoplankton absorption from blue to green and its magnitude vary with size class. And you can see a reasonable example of this, and you've seen others and probably have your own over here in this plot. And the idea is that if you have a satellite-derived spectral satellite-derived measurement of phytoplankton absorption, you have all the information you need to gauge this relative slope and derive the magnitude. And then there are simple separations. In this case, if the magnitude of phytoplankton absorption in blue is greater than this threshold value, it's microplankton. Again, the beauty of this is you can derive it from satellite measurements. But think back to everything you've learned about what's going on in the field and what's going on with the satellite. Think about if this is the right approach for you. Okay, enough with abundance methods. Any questions so far? And I can't see hands raised or anything, so just jump in, or somebody jump in, or just say no questions.
How is he saying that if it's not micro and not pico, it must be nano?
Basically mass balance, saying that in a relative sense, since these are all fractional, if it doesn't fall, if it doesn't meet this criteria, which is the upper boundary condition, or it doesn't meet this lower boundary condition, then it has to be the one that falls in the middle.
So Jeremy, I would like to add another question.
Sure.
Comment. We know there's a relationship between size and chlorophyll. But way back from work, Rico and others,
Yep.
Chlorophyll itself is an indicator of the underlying size. You know, with a relationship on the order of an R square of 0.6 or 0.7. Is anybody checking to see that their method is better than just doing it with chlorophyll alone? Or that it improves the information. Actually, we find places where chlorophyll will tell us it's big ones, but their method showing that it's small and it's really small.
Well, so I think what you're really touching on here is the improved information part of your question.
Yes.
So if you search literature, I'm sure many of you have done this, you will find there are any number of intercomparison papers with a new method that will say, I can do better than a standard chlorophyll-based algorithm in my little neck of the woods. And what they're doing there is effectively just assessing performance relative to whatever in situ data set they have, and we'll get to that. And using some statistical metric to either declare success or not. So very few of these get into metrics of information content or derive any useful information on why performance is better or worse. And so I don't know if Emmanuel, have you gone through information content and the course of
A little bit. Actually, Cal's paper. Yeah.
Yes, that's right. So this is a great topic for this student body to start considering, because the literature is really Spartan on this. Would you agree?
Yeah.
Other questions? All right, onward, because I know I've been between you and lunch. Spectral methods. All right, so in the case of a spectral methods, what you're really looking at is variations in spectral shape. And this can be in remote sensing reflectance or inherent optical properties, and relating those variations in the community structure variations. So the nice thing about these is that unlike abundance approaches, if you have a common total biomass, but a varying spectral shape, and assuming that what you're searching for has a contrasting optical signature, then you are no longer limited by the ambiguity imposed by differences in two different groups with a common total biomass. The difficulty becomes, and Colin alluded to this earlier this morning, is that you can be confounded by variations in spectral characteristics that are going to change because of growth conditions or nutrient availability, ambient light conditions, different mixtures, different places in the water column as you're trying to come up with a remote sensing relevant value. So there's a lot of power in all of this, but they're not universally the solution alone because of the ambiguities and the fact that any spectral inversion in a reverse inverse method can be an ill-posed problem. So let's start with two that take satellite-derived radiances and go directly to either accessory pigments or size classes. The first, Jiaju Pan, what year, 2010, series of algorithms for the northeast coast of the US that operate exactly like our empirical algorithm. Look for a statistical relationship between a band ratio of reflectances and a concentration of whatever we're looking for. So really just extending the work that, has been Howard Gordon and J. O'Reilly and others have been doing by just band ratios to pigment. And there are line height methods to get to this as well. A number of these exist. Schwann Hughes group, University of South Florida has a bunch of very nice ones, many others. This is one example I'm more familiar with where you are relating a line height in the near infrared to the presence or absence of cyanobacteria. So the way this generally works is you take either your reflectance or your normalized water leaving radiance or your remote sensing reflectance spectra, and you're looking for curvature around a target wavelength. In this case, it's using Maris and its 681 band, which is sensitive to presence of cyanobacteria. And the idea is really simple. If there is a positive line height relative to the baseline between two surrounding bands, there's no bloom there. If there is a negative relationship, the bloom exists. So this is binary. It's there or it's not. Now, this work has been extended to try to relate these line heights to some geophysical parameter of interest, whether it be a chlorophyll concentration or a cell count. Now, try to imagine what would have to happen under a diverse array of conditions for that to be a meaningful metric. So the way this project got around it is just to retreat to World Health Organization stoplights. Green, body of water is good. Yellow, hey, someone should check it out. Red, please don't swim there. And that was simply done by relating the peak of the line, the size of the line height to severity. But that said, again, just taking an optical measurement and coming up with some indicator of presence or absence of one particular phytoplankton group. All right, moving on. So another remote sensing reflectance way of providing the estimate of dominant phytoplankton functional type comes out of Severin Alvain's grants. This work has been building for over 15 years now. The way it operates is that they take global climatological maps of Modus Aqua in this case, and they group different remote sensing reflectance spectra into different chlorophyll bins. So what you're looking at over here is an average satellite normalized water level reflectance for a certain chlorophyll level. And you can see that the shape changes as your chlorophyll increases. The algorithm operates by suggesting that deviations from this average spectra can tell you something about what phytoplankton community is in the water. So in operation, they have this library of averages per chlorophyll. They take a daily satellite pixel estimate of chlorophyll and remote sensing reflectance. They find the corresponding average, and then they find the delta from that daily observation from the average, and they derive an anomaly spectral shape, which you can see here. And the general premise is that this spectral shape in anomaly space will change as a function of these four functional type. Okay, so a totally different way than the empirical ways that you just saw before. But again, yet another flavor of doing this. All right, moving on. Methods to go from total absorption to accessory pigments and community structure. In this case, this is dovetailing into exactly what you just heard from Colin, refers to the same two papers where you're relating pigment absorption features to their presence. Again, you've seen the Catlett and Siegel paper where there are relationships between spectral derivative absorption signatures and the present phytoplankton community. And then the Gaussian decomposition that you just learned about. In this case, you're seeing Ali Chase's work again, where you're reconstructing a total absorption spectra from contributions of different pigments defined by their Gaussians. The reason I bring these up is you can do this in two different remote sensing spaces. You can do it where you take an estimate from space of some absorption spectra and then apply these, or you can actually start embedding them into inversion models, which we'll get to next. Okay, so in this case, what we're really talking about is using a combination of inherent optical properties with satellite derived radiances. So this is another example of what we were just talking about. So if you think back to your inversion modeling lecture with Colin, which I believe was lecture 23, in that case, you were probably solving for 3 or more dominant magnitude retrievals. So again, remember, you're defining spectral shapes here in this kind of inversion scheme, and you're retrieving the magnitude of the eigenvalue that corresponds to the eigenvector. So you're solving for the magnitude that corresponds to the spectral shape that best allows you to reconstruct your input spectra. So what Colin and I did in this paper was simply to take a 4-parameter model, so an estimate of diatoms and noctiluca, that heterotrophic dinoflagellate that she mentioned an hour ago, so, and see if we could use an inversion model just to solve for 4 parameters instead of 3. Now, I know in the work that you're doing now, you have access to hyperspectral information, and you may be asking yourself, why just 2? Why not more? Keep in mind, our heritage satellite instruments have 5 to 6 useful visible bands at best. So in this case, if you're looking at the solid lines here, this is the only information you have from Modus Aqua to actually tease apart the two contrasting signatures here. Another example of this, just to show you that you don't have to be limited in how your inversion gets embedded, comes from Anik Berko and Oriacciati, where what you do is you define two different size classes of phytoplankton by a spectral shape parameter. So just like this other approach, you're defining what your spectral shape, your eigenvector for the phytoplankton community is, but rather than just solving for the magnitude, what you do is solving for the relative fraction of each of them. So you can also envision taking Ali's work from the previous slide and then putting that into an inversion type model. And in fact, she did in her 2017 paper. So there's a lot of ways that you can combine estimates of remote sensing reflectances and embed them into these inversion type models by varying how you treat absorption. All right, last but not least here, what do you do with backscatter? So, well, the most common work that you may have seen or not, it comes from Dave Siegel's lab and Tiho Kostadinov. His purpose was to estimate the relative fraction of three size classes for each pixel. So the beginning of all of this is using a separate algorithm to derive backscattering spectrally, and thus an independent assessment of backscattering spectral slope. And the predominant approach to do this comes from Loiseau and Stramsky. They have since written, I think, a 2018 or 2019 paper that updated this. But not a lot of work has gone into actually deriving backscattering spectral from space. Of course, even this work assumes that it is a power law representation of the spectral shape. Well, the way this approach works is they ran a number of me-theory simulations and came up with the relationship between a power law slope of the distribution and backscattering spectral slope, and then power law distributions with the actual particle size distributions for this. So the way that this approach works is if you can get to backscattering spectral slope from space, you can come up with power law PSDs. If you go that, then you can actually get into distributions, the particles. And so this was actually the first ever attempt to get to PSD slopes from space, as well as biovolume distributions and so forth. But think of all of the steps that went into this. Groundbreaking, an immense amount of work, but still start asking yourselves as you move forward, what needs to be done to move beyond this? Is me the best way to represent a phytoplankton community? Now, maybe it's not. We most certainly know it's not, but what do you do about that? What do you model next? All right, my biggest point here to wrap up this section of the talk is that it's kind of the Wild West in terms of everything that has been done to derive size classes and phytoplankton community structure from space. Again, we're not minimizing the level of efforts. It's been heroic. And all of the PIs and authors of this have had special questions they want to answer. But the result of that has become, this diversity in methods that are out there, all with their strengths and weaknesses. So you need a critical eye for all of this. If you don't have one already, I hope you do now. So those were really only the approaches that dealt with remote sensing reflectances and derivative products. As you might be expecting, and this is a question I would ask if I were walking around, what's missing from all of this? What other information is available that can make this better or give you more information to start whittling down these broad dynamic ranges of assumptions that all of those approaches need to whittle down into a smaller, more manageable, possibly more appropriate series of assumptions? Well, first one is environmental conditions. And it's only been recently, but they're starting to be considered more and more often. Anybody ask a question of the class? On what kind of environmental conditions do you think you can measure or model from space that would be meaningful? Sorry, I'm having trouble with hands. Just yell out.
Temperature.
Sure. Okay.
Temperature.
Ready?
Temperature. Now, is temperature available on every satellite?
No.
So what do you do about that? Oh, you have to bring in the data from somewhere else. What else?
Wind speed.
Okay. What would wind speed help with?
Mixed layer depth.
There you go. Report, can that be measured directly from space yet?
Yeah, but super low resolution.
So I guess what I'm kind of getting to here is start thinking about Kurt's lecture where he focused a lot on the different ancillary data that needed to be brought in here. It's not a problem, it's just something you need to be aware of. And not all ancillary data is available on all of the spatial and temporal scales that you might have for your neck of the woods as well too. Anyway, good answers. There are lots more, but I don't want to keep you from eating. One thing that's really only become popular in the past couple of years is to start using emerging computational methods and other types of math to derive these. So nothing we talked about so far really got into EOFs. Super psyched to see, I think it was Luca talking about that earlier this morning, neural networks, Bayesian theory, artificial intelligence, and machine learning. They're all starting to emerge. So keep that in mind as you develop your methods. And again, they all have strengths and weaknesses. Niba's work here is one of the first that actually tries to use machine learning and artificial intelligence to derive certain inherent optical properties and concentrations in US inland lakes. But again, this is a garbage in, garbage out. How good does your field data need to train all of this? Does it represent all conditions that you might have, problems you're going to have to solve? And what's really, really emerging, at least in in our lab and within the science team, is the use of not just neural networks, but Bayesian methods as well. And you can embed these into your inversion and mathematical models too. And it's a completely different way of thinking about how to handle prior information and uncertainties. So there's a wide open field here in computing technology and ideas that are only just now starting to be applied to inversions of phytoplankton community structure from space. And I'm sure you've covered a lot of this in the other lectures because I know it's happening for in situ methods as well. So sorry if I'm preaching to the choir here. Okay, any questions on those methods, or we'll move on to the second part of the lecture. This goes a little faster. Okay, well, the second thing I want to talk about just kind of leads into uncertainties and their sensitivities. And I view this as a pretty substantial gap that needs to be addressed in the next generation of use of these approaches. So hopefully this will inspire you in some future work. What we know now is that all algorithms use some form of derived product to make some kind of a priori assumption. And few of the papers that exist include a real robust analysis of the sensitivity of the model outputs to their inputs. And we're not even talking now about considering uncertainty propagation of all the different measurements. These are just simple uncertainty analysis. Like if my atmospheric correction is off by this much and creates relative uncertainty in my chlorophyll of this much, how does that propagate into some sensitivity to my actual chlorophyll to PFT relationship? Those errors aren't typically propagated. And so what we really don't know is how sensitive are the abundance methods to uncertainty in their inputs, the example I just gave you, and how sensitive are the spectral methods to uncertainty in remote sensing reflectances and derived phytoplankton phytoplankton absorption and other parameters. And just to give you two quick examples of how uncertainties can add up really, really quickly. What you're looking at on the left is a complicated plot. It now appears in an IOCCG report on uncertainties, but it's intended to show you how an error in the band ratio of remote sensing reflectance propagates into the retrieval of a band ratio chlorophyll algorithm. So what you're looking at on the x-axis is just the band ratio. On the left y-axis is the chlorophyll concentration, and that's the black line that goes down here. And just broadly speaking, here is where eutrophic might be designated and the leucotrophic might be designated. What you're looking at the right-hand side y-axis is the percent differences in the chlorophyll retrieval given a delta in the maximum band ratio. And so if a maximum in an oligotrophic condition, if my maximum band ratio is off by plus or minus 10%, as represented by the red lines here, my chlorophyll retrieval will be off by about 50%. This is far more forgiving in the mesotrophic range, and to a lesser degree in the eutrophic range. But I can tell you, having seen this, how the sausage is made, and you should probably be able to intuit by now, having done some atmospheric correction of your own, that it's not unreasonable to expect some kind of uncertainty in this ratio on the order of 2 to 5%. So now ask yourself, if that translates into a chlorophyll difference of somewhere in the 10 to 20% range, what is the impact on your retrieved size class or functional type? Moving to inversion algorithms, this shows up in the paper that defined the GIOP, which is one framework for an inversion algorithm. Part of that analysis was to start varying the input spectral shape into an inversion algorithm and see what it did to the retrievals. So in this case, you're taking the backscattering spectral slope that you're defining before you conduct the inversion and altering it by plus or minus 30%. You can see that the retrievals here in median percent difference result in 5% or so across the board. How would a 5% difference in your backscatter and retrieval impact those PSD maps that I showed you previously? That work really hasn't been done yet. And you can see, based on some other decisions you make, those uncertainties grow. So again, all good work, but something that needs to be considered that's not being considered yet. And bringing you all the way home here, remember that all ocean controller approaches start with just remote sensing reflectances. So what we're showing here doesn't even touch on the impact of atmospheric correction on any of this. And now start thinking about a hyperspectral atmospheric correction, where you need to deal with spectral features and absorbing gases that might make small wiggles of imperfection in your derived remote sensing reflectances. What is this going to do? This kind of uncertainty propagation and analysis needs to go on. All right, we're going to come back to that a little bit. Now, this is touching more in line in what you just heard from Colin. Most folks are using proxy data sets for our validation. Again, this is another gap in our ability to do this perfectly well. You already know all of this, but there are a ton of different ways of measuring functional types or size classes in the field. You've had experience with this the past 3 weeks in your own lives. I'm bringing up chemtax and diagnostic pigment analyses one more time here, not to describe how they work, you know that now, but to point out that most heritage approaches have all been tuned or validated by one of these two methods. And if you go back to those 2 papers that you saw before, and you take a look at this summary of validation exercises, just scan it really quickly. You can see the validation data source as of 2017, HPLC pigments, and on and on and on down. And the table's 2 pages long. So this is neither here nor there, good or bad, but it's something that we need to consider in how field measurements are made and how we interpret our evaluations and our performance evaluations of these satellite algorithms. Now, every author acknowledged, everyone who used HPLC in all of those papers, they weren't highlighting it as basically saying, this is the be all end all. We are doing this perfectly. They want microscopy imaging, IFCB, flow cytometry, enumeration of cells. But they were limited by the fact that those measurements at the time were currently limited, whereas HPLC were the most abundant and globally distributed. You can see that if you look at the CBAS map that was as of 2019 that shows distribution of HPLC measurements available for algorithm development and validation. Now, the other reason I'm bringing this up is everybody talks about global distributions in abundance, even when talking about HPLC measurements and other technologies. But if you look at 1 year of discrete samples contributed to this database, it actually distills down to this map. And the point here is that it is neither spatially nor temporally as distributed as we think of. So you need to start thinking about what does this mean in terms of your performance assessment, your consideration of uncertainties, the portability of your approach. And are there other technologies out there that can be used, things that are autonomous, underway, Antara, or the AMT cruises that go on, that can be used to start filling in these gaps. Now, they'll all have their own strengths and weaknesses. Again, things that you need to be considering. And that kind of gets me down to a take-home question that I have for you. So you know that there's a ton of ways of making a measurement in the field, but you also know that there's a ton of degrees of separation in what the satellite is measuring and what you're actually measuring in the field. Given what you know about all of this, how do you prepare your in situ data for a validation satellite exercise to get as close to apples as possible? You saw previously that these satellite measurements are coming up with, yes, maybe a measurement of an accessory, concentration of an accessory pigment. Got it. We can make that direct measurement in the field. But a functional type, what are the units of the functional type? They all vary from approach to approach. Particle size classes are typically done in percentages, right? Or some kind of size distributions. Well, how do you take all of this different information and relate that information into the same thing that the satellite is measuring? So here is just one example. It's getting back to that cyan line height that I was mentioned before. This is a map of, I think, a lake in Wisconsin. And managers are basically using it to say, if I have this cyanobacteria index, which is just a line height, and it's unitless because this one is derived from reflectances, surface reflectances. Yeah, you can see where that line height is big versus little. The reds indicate something is there. Purples indicate either it wasn't a retrieval or nothing is there. But how do you go in the field and validate this? How do you collect enough information to relate it to a biogeographical variable of interest? And it might not sound like a problem, but if an agency like the EPA or NASA is putting this out there, when you think about the watershed manager who is actually trying to make decisions about going into the field and collecting a sample, and they don't know which lake to go to, so they're using satellite data, do they care what an optical measurement of CI means? No, they want to actually relate this to biovolume or chlorophyll concentrations to something meaningful. So now you have this added step of somehow relating the optical measurement from the satellite to a biogeophysical metric of interest. It can be done, but it's not done conscientiously. And a lot of data isn't available to do it well. So another problem, another gap for you to think about. Now, there is positive and light at the end of the tunnel here, and I particularly like highlighting students from the class that have done something that has, really changed the way at least some of us think about all of this in terms of rigorous validations and metrics of performance session. You've heard the name Sasha Kramer before, but she and Colin and Heidi put a paper out in 2018 that did a very nice job in my mind of taking an existing approach, modifying it to suit a particular need to answer a particular question, then questioning some of the assumptions that went into it, and then reviewing strategies and presenting them, the good, the bad, and the ugly, into how this algorithm should be conscientiously applied and validated. So there are others that have emerged, but again, one that came out of our class, and I thought it was a really nice one, and it provides hope for me that you guys are going to all pick up the ball and do amazing things with all of this. But getting back to the gaps, well, we're not super with uncertainties. We don't have direct proxy. We are only using proxies for validation. Combining these gaps makes this even harder. So one last thing that probably most people don't think about, and then I'll let you go. What about satellite data compositing? And I don't know whether you did this in your labs or not, But what I'm talking about here is the treatment of satellite data from the original projection, the level 2 part, pixel, into some kind of temporal or spatial average. What happens to the data? So we're going to consider horizontal, temporal, and vertical resolutions here, and we're going to go all the way back to the Arabian Sea, which you learned about. This is a follow-on study to what Colin discussed in the Thibodeau paper. So I want you to focus on this Cape Cod-shaped Noctiluca distribution that occurred, and you're looking at chlorophyll here. This is the level 2 image. It's 1 kilometer. It is the best thing we can get from Modus Aqua at the time, but it is the closest in space to time as we have to reality here. Well, I can tell you from experience, and any of you who have looked at satellite data, well, it's a cloudy world. And there are sun glint, and there are gaps in satellite measurements, and there are algorithm failures. So you'll have need at some point in your career to do some averaging. So let's first look at what would happen if we binned this level 2 file into a larger projection, which you would do for a global map or a regional map or something like that. Well, if you go from 1 kilometer to 2 kilometers, you can still start seeing features here. But I want you to take away that as you start to get into bigger pixels. So let's say if you were doing a study on a global scale or a big ocean basin scale where you're using a big global map, not a series of satellite swaths to conduct your research, well, your pixel is your Noctiluca feature here is starting to get diluted. Okay, and a lot of that is just because of the way the averaging of these projection works, but your answer is going to change. The number you get here in the 9 kilometer projection is not the same number you're going to get here in the original level 2 file. The problem gets even more distilled if you start doing temporal resolution. And trust me, binning temporally is something you will encounter at some point in your career if you use satellite data. There is no way around it. Again, it's a cloudy Earth. But if you look at the original file and then you consider an average the day before and the day after, so this is a 3-day composite, this is what it's going to look like. And the features are already starting to distill and change their shape. This is a plus or minus 7 days, so now it's a bi-weekly average, and then this is a monthly average. So if you're looking at a monthly average, a monthly global average on chlorophyll distribution in the Arabian Sea, you don't see this Noctiluca feature anymore. So you need to start thinking about, well, what spatial and temporal scale do I conduct my analyses from space on top of everything else? And then don't get me started on vertical resolution. In this case, I think this actually convolutes a bit how one takes your in situ measurement from any of those different instrumentation suites that we mentioned before and you've been practicing with, and start taking a depth profile and somehow integrating it into something that the satellite actually sees. What the satellite actually sees is some optically weighted version of the first optical depth. So contributions made near the surface are far more important than contributions made at depth in a relative sense, except for when at the bottom of this first optical layer, something interesting is happening that is more important than what you're seeing at the surface. And there's 30 years of papers on all of this. So if we take this case study of you only made 2 measurements, and the first is right near the surface, and the first is right near the bottom of the first optical depth, and you just average them, you're going to come up with a value that is 1.25 in this theoretical case study. If you're only using the surface value, it's going to be 1.5 milligrams per cubic meter. But the thing that the satellite is close most to seeing is somewhere in between, which is a little closer to 0.1 milligrams per cubic meter. And there has been ongoing, more recent debate on the implication of this, both for algorithm development and for validation, but it is something that needs to be considered. If for your study area, you can prove that it doesn't matter, Yahtzee, no problem. But in a lot of places in the world, it's going to. And it also gets into how do you devise sampling strategies in the field that can help you address these things when you go back to your office and you start thinking about the relationships between what you measured in the field and how you're going to use it in the satellite paradigm. Okay, so in my mind, this is a third gap. And when you combine all of these three, yowza, and now think about when you're doing this for a multitude of different satellite approaches. There's plenty of work to be done. I have the utmost faith that you will solve all of these problems in my lifetime. So never give up and keep your eye on the prize, which is this global map. I hope you've seen over the course of the weeks the 20-year satellite time series from CWIS Modus Naqua. In fact, you did during Kurt's lecture that shows distributions of chlorophyll changing over 20 years. To me, that is a masterpiece that rivals the moon landing, for Earth science. To basically compress your senses, bring them into space, and observe 20 years of change in the ocean is just absolutely remarkable. What you're looking at here is from, I believe, the ECO2 model, Woods Hole, other places, that produces something similar for 4 different phytoplankton groups. We can't do this from space yet. We can do it while modeling. My challenge to you all, with the emergence of PACE and other instruments that can contribute, is take that amazing time series that you saw over 20 years and start thinking about how to make it with phytoplankton functional types, community structure in mind. Because we all need to know where the carbon is going. The IPCC report came out yesterday or the day before. We need to be doing this, and we need you to be doing this. All right, with that, I'm done. I think you have lunch in a few, and wish I were in person. Thanks for abiding a Zoom lecture over the course of the weekend. Questions now or later, whenever you want.
Answers.
Sorry, if someone's talking to me, I can't hear it.
Jeremy, if you have a particularly cloudy region, what is the best way to deal with getting good matchups to compare in situ versus satellite data?
Satellite can't see through clouds, so as you know, so there really isn't a robust way of doing that. There have been some studies over the years that have attempted to gap fill, using various statistical techniques, and say, if I know something about surrounding pixels or the day before or the day after, then I can make a pretty good estimate of what might be under the cloud. That then becomes kind of a religious question. And I think it would mostly depend on your knowledge of that region. And, so think about how fast certain communities can overturn, double in size, go away over a given time period. You'd have to feed that into your trust in doing any kind of gap filling. So in lighter clouds, if you had something that can penetrate clouds like LiDAR, then you have a better shot at this. That comes with its own limitations and strengths as well. Frankly, I think the best long-term way to solve this is you don't start thinking about NASA-like observing systems being a satellite alone or a series of satellites. You start thinking about how to couple field programs with suborbital things that can fly below clouds and satellite measurements and models. And you start thinking about this a little bit differently than there's a one size fits all. So I'm sorry, that's not a really awesome answer, other than I'm not a huge believer in, if the satellite doesn't see it, then I can truly assess the performance of it.
Thank you, Jeremy. That was an excellent answer.
Jeremy, Kurt Mobley here. I think I'm invisible to you all, but
Always in my heart, Kurt.
you made the most. Yeah, that was scary. You made the most amazing thing in this simulation here is the westward propagating waves coming off the Galapagos Island. And yeah, that streak there, is that due to the Galapagos Islands putting iron in the water, which are then growing the phytos as they move westward?
You know what? So I've always attributed to being part of the equatorial upwelling system here, but I am not a strong physical oceanographer. I might have to defer.
I think that's correct. It's an upwelling effect. Because I think that there's a lot of iron coming in from the deep water along the coast of South America. And there's definitely upwelling and island effect.
It is fascinating how with that, you can see that you can see this in chlorophyll, but you can, if you believe the model, that a whole different community exists there because of this.
And that's the question that needs to be validated.
That's right. Do we believe the model? Yeah. What else?
So what do you think about multi-satellite compositing? Think like globe color.
It addressed a different question that I think can be powerful if done well. So the strength of doing that is in the auspices of something like globe color. You're considering satellites that have different swath widths and they view the world at different times. And the advantage of this is that if satellite A doesn't see something on day one because of a cloud or because it's just the swath didn't hit it, then satellite B can fill in that gap potentially. And so you would still have the spatial problem because all of these satellites typically measure life at a different pixel size. So you can't be necessarily as small as 1 kilometer because you might have something that's on edge of scan that's slightly bigger. You still go up to 2. But okay, let's accept that. The problem that then becomes your number one concern is intercalibration across the multiple satellite instruments. And I can tell you from the experience that even when you have identical instruments, like the 2 MODISes, one on Terra, one on Aqua, the 2 Olchis on Sentinel 3A and 3B, and the 2 Virses on SNPP and NOAA 20. These are tended to be cookie cutters. Cookie cutters don't give you the same answer. They are very difficult to intercalibrate, and a lot of investment goes into that. When you're going from a Virus to a MODIS or a MODIS to an Olchi, that problem amplifies because there are different instrument characteristics that feed in to what you have to do for this intercalibration. Now, it's not impossible, and groups have done well. Fred Malin has nice ways of assessing biases and mismatches, but you can't ignore those biases and mismatches when you do this. Now, tangential to all of this, I am really intrigued about bringing this to a local scale and starting to use high spatial resolution instruments like Landsat or MCI in combination with the 1 kilometer instruments. Because I think there's probably a lot to be learned there in that kind of combination. And then, of course, if you bring in other measurement types like LiDAR or polarimetry into ocean color, I think there's a ton to be learned there too. Sorry, another long answer. That's what I get. I'm alone in the house, so I'm basically talking to.
And I had a question about using different satellites. So, do you think if we can that we can use different satellites because they have different bands to have higher spatial resolution? Yeah.
So can you increase the spectral resolution by putting together satellites that have different bands?
If they are perfectly intercalibrated, I think you are good to go.
Of course.
Yeah, I mean, in all honesty, the closest example I have to this is the MODIS has what they call ocean bands, land bands, and atmosphere bands. So this is a series of bands from the same instruments. from the same singular instrument. And if you look at the ocean color bands, which are all the 1 kilometer bands, they are the most suited to do what we do. And they're all at 1 kilometer. There are 2 land bands at 469 and 555 that fill in spectral gaps that are desirable. These bands are 500 meters instead of 1 kilometer, and their performance is different because they were not because anybody messed up, but because they're designed to do different things. And as we'll talk about tomorrow, you make choices based on your discipline in how your satellite performs. The ocean is very dark, so you need to have something that can respond to a very dark signal, whereas land is bright. So what I'm saying is that even those small differences add up to challenges in intercalibration of the land bands for use for ocean applications. And there have been some successes and some failures in using those spectra for derived geophysical products. So I think the problem grows if you try to increase spectral resolution using 2 instruments that haven't been treated for some of their differences. Now, all that said, I think it depends on your question. Like if you are studying a really small body of water or something that really requires the use of something like Landsat where there aren't many bands to choose from, if you're careful and you perhaps use maybe like a Bayesian technique that can account for uncertainties and priors and things, then maybe bringing in one of the 1 kilometer instruments with greater spectral resolution can teach you something. Like, I don't want to discourage it, but I think you need to be very conscientious about how you would treat systematic and random uncertainties and prior information in really trusting, how this combination would yield something that you can believe in on the far end of the derivation. So, does that make sense?
Yes. Jerry, this might be making that problem twice as bad, but I'm curious. I know like the old Planet doves were pretty bad spectrally, but they just launched like 50 super doves, which is supposed to be way better. I'm curious if there maybe lessons learned from Seahawk, and is there any plan to experiment with daily 5 meter data from the super doves, or just any similar CubeSat?
I really, really hope so. Getting back to observing systems need to change their philosophy. I think because of the successes of things like Seahawk, and hey, there are performance issues in Seahawk, because I think they built the instrument for $200,000. I mean, that's light years different than something like Pace's Ocean Color instrument, which is $250 million. So there's a place for all of this. Again, I think that depending on what you're interested in, these constellations of small sats, they're a great idea. Just don't use them for climate work, because they're all going to degrade differently because they're not designed for long lifetimes. And the instruments will all behave a little bit differently. I mean, maybe looking for super global long-term trends isn't what you should be doing with them. So fly something like Pace at the same time to do that. But if you are really interested in a small neck of the woods and you understand that area and you need routine coverage, I definitely think CubeSats are a great way to go. And then fly a bunch of drones under them too. So it doesn't make the problem worse. It just changes the way you have to look at the result, I think. And you have to temper your expectations for what they deliver.
Right. Thanks.
Okay,
All right.
excellent. Thank you, Jeremy.
Yeah, I hope it was okay over Zoom. And if it wasn't, let me know before tomorrow. So
All right,
all good.
have a great
Lunchtime.
Thanks.
And speaking,
Bye.
Hi, pal.
speaking of Seahawk, the water sent overflight over this region, and Sarah and the Sarah River sent us an email about it. If you're interested in that data, we can create a contact and for hear how it goes down there.
with the CR. So if you're interested, by all means, we'll get you connected with the